to the organizers for giving me an opportunity to talk. I'm very happy to give this talk, which is based on work I've been doing recently with Shinan from UNC Chapel Hill and Misha, Stefano, and Hongi from University of Illinois at Chicago. And this work is based on these references and as always, work in progress. So one of the major outstanding problems right now in theoretical nuclear physics is mapping the phase diagram of QCD, and in particular understanding the phase transition, the properties of phase transition between the deconfined quark-gluon plasma phase and the hadron gas phase. A particular outstanding question in this search is whether there is a critical point that separates a smooth crossover and a first order phase transition. And if so, where it is located. And in the search of the critical point, fluctuations play an important role because their magnitude grow as one gets closer to the critical point. So experimentally, the search for the critical point is done at the relativistic heavy ion collider and other facilities in Europe that will hopefully start collecting data soon. And in particular at RIC, the idea is to span different points or different trajectories in the phase diagram by tuning the collision energy, and in particular lower the collision energy, the higher the chemical potential is. So each collision transports one from here to some point here in the phase diagram, and right after the explosion, as the system expands, it cools down, it sort of impressionistically traverses a trajectory that looks like this. And the idea is to sort of span the phase diagram by the different trajectories like this and look for signatures of the critical point. So one, as I said, because the fluctuations grow near the critical point, these observables are higher point correlation functions of the number of final state hadrons. For instance, the fourth cumulant is sort of the canonical observable in the search for critical point. Qualitatively, it has some shape where as one gets closer to the critical point, one expects a peak in the fourth cumulant. And in fact, an intriguing early sort of signature experimentally in this observable shows some form of an enhancement, but of course there are large error bars and more data is on the way. But this is a sort of an intriguing hint, as they put it. Okay, so our job as theorists to make more quantitative predictions on these cumulants. For instance, this particular shape was obtained by taking an equilibrium, taking the fluctuations to be equilibrium fluctuations. But we know that the quark-gluon plasma that's created in heavy ion collisions evolve in a dynamical environment. Therefore, it is very important to have a theory which incorporates dynamics of fluctuations, both near and away from the critical point, so that we have a good theoretical control over what's going on. And because in the region that I'm interested in, quark-gluon plasma, is described very well with hydrodynamics, I will be focusing on hydrodynamic fluctuations. So in a nutshell, hydrodynamic fluctuations can be understood in the following way. So a hydrodynamic system is composed of infinitesimally small fluid cells, but each fluid cell itself is a thermodynamic system which is in equilibrium. It has many macroscopic degrees of freedom, and the values of the macroscopic variables, the energy density, the density, and so on, fluctuate at each cell. And these fluctuations can be incorporated in the hydrodynamic evolution as a local noise. Okay, so one way to incorporate these fluctuations is to promote the hydrodynamic degrees of freedom to stochastic variables, which throughout the evolution get some kick, which is given by noise, and the magnitude of this noise is set by the transport coefficients, some combinations of viscosity and conductivity, which is enforced by the fluctuation dissipation theorem. So numerically, one can do this and simulate a system, a hydrodynamic system with noise. However, the magnitude of this noise also scales with 1 over the fluid cell size to the power 3 house. This follows from the central limit theorem, and because the fluid cells are infinitesimally small, this creates a numerically large noise, which is sort of sometimes problematic to implement numerically. But an alternative approach that I will take is instead of solving a stochastic system, solve a deterministic system where the ordinary hydrodynamics, which in this language can be thought as an evolution equation for the one-point function, is supplemented by the evolution equations for the higher point functions, the quadratic fluctuations, the skewness and kurtosis, and so on. Okay, so that's that. So what do we expect from these evolution equations? At very small scales, these fluctuations are pinned to their equilibrium values, so and completely determined by the equation of state. However, when I go to larger distances, then different parts of the fluid, of course, have different temperatures, different pressures, and so on. So it's out of equilibrium at that scale, and the fluctuations are trying to reach their equilibrium values, but there's a competition between the background flow, scale of the background flow, and how fast the system equilibrates, because the system equilibrates through diffusion, which takes finite time. That time can be estimated as the typical system size divided by the speed of sound. And because the equilibration happens through diffusion, given an amount of time, only a finite region in this fluid is equilibrated, which is given by this equilibrium scale. So it's useful also to package these fluctuations in terms of their wave vector, which is the Fourier transform of the sort of the spatial scale of the fluctuations. And in that scale, the typical wave vector where the fluctuations start to fall out of equilibrium is given by 1 over L equilibrium. So I'm interested in the dynamics that happens here. Okay. So the basic physics is how these fluctuations relax to their equilibrium values. Therefore, oops, sorry about that. Therefore, the sort of the typical expectation is that I will have some hydro equations and have new degrees of freedom now, the 2-point function, 3-point function, and whatnot, and they will satisfy some equilibrium type, equilibration type, or relaxation type equation, which sort of schematically looks like this. And of course, the higher point functions will also appear in the constitutive relations in hydrodynamics, because the average of the flux is not necessarily equal to the flux as a function of the average hydrodynamic variables. That's why there will be sort of the 2-point functions, 3-point functions, and so on will also sneak into the hydro equations. So this approach has been taken in the context of relativistic hydrodynamics by Akamatsu, Maziliauskas, and And Veracini in 2016 considered a particular boost invariant plasma, and then various other groups, including us, sort of generalized it to more general systems, and we worked out most general formalism with arbitrary background and so on. And in non-relativistic context, this actually goes back to 1970s, the work of Andre. Okay, so the general evolution equations for the 2-point functions are sort of complicated, but they can be packaged in a nice sort of simple way, which describes essentially a kinetic equation for phonons. So on the left-hand side, there's some Liouville operator that involves all sorts of inertial forces, rotation and expansion and all that. And on the right-hand side, there's basically this relaxation terms. So you can find the details in the references. And there are also other modes which are slightly more, more mysterious than these sound modes. These are like phonons which have sort of zero effective speed of sound. These are purely diffusive modes, and these correspond to fluctuations of entropy, entropy transverse velocity, and velocity, and they have again a similar sort of Liouville operator on the left-hand side and some relaxation terms on the right-hand side, and in general these are all coupled to each other. Now, one sort of application of this deterministic evolution of fluctuations is one can actually approach the critical point. So as one approaches the critical point, the correlation length becomes larger, and sort of hydrodynamics for above certain frequencies break down. And this breakdown happens when the two-point function associated with entropy actually falls out of equilibrium. And this happens when the evolution rate of the system, which is given by C cube or 1 over C cube, exceeds the relaxation rate of this mode. And in order to now describe the physics above these frequencies, one has to take into account the relaxation of, or the dynamics of this MM mode. This was studied by Misha and Yin in 2017. It's called Hydro Plus. And there are some applications of Hydro Plus to sort of different sort of systems numerically that you can look at it here. But even at larger frequencies, now the other modes also fall out of equilibrium. Therefore, in order to describe the physics here, one needs the relaxation or the time evolution of all the other modes as well. And this is what we call Hydro Plus Plus. So another advantage of this deterministic approach is that one can actually do some sort of form of OPE to isolate the UV divergent contributions to the fluctuations, which are the equilibrium fluctuations, and local contribution, which renormalizes the transport coefficients, and entirely focus on the finite, the actual physical contribution, which are finite, which are known as the long time tails. And one can actually derive these fluctuation evolution equations for the finite quantities. So numerically, you don't have to deal with any UV singularities. And I'll skip this. One can study the long time tails in a general system and so on. So let me, in the second part of the talk, briefly talk about the higher point correlation functions. So this was all about 2-point functions. Let me now generalize this. Okay. Now, it's easiest to illustrate the general strategy in an example where I have a discrete set of variables as opposed to fields. But then I will generalize this this general sort of formalism to fields, or take the continuum limit if you wish later in the talk. Okay, so the example, the setup is a Brownian motion, which is captured by this Langevin equation, where I have a drift term, which is sort of the hydro part, if you wish, and then there's the noise, which are the random things. Okay. Now it's useful to put the drift term into what I call an Onsager form, where it's given by some matrix times thermodynamic force, which is given by the derivative of entropy with respect to the variables. And for the rest of the talk, I will use this notation where I denote the derivative with respect to qi as a comma I, sort of this GR-inspired notation, which will sort of which compactifies the makes the uh, um, notation more compact. There's no compactification space time or anything. Anyway, so this is our setup now. Then this matrix can be split into the symmetric and anti-symmetric parts. So the symmetric part describes the dissipative contributions, and of course, as dictated by the fluctuation dissipation theorem, it's proportional to the noise term here. And then the anti-symmetric part is non-dissipative, and that describes sort of the Hamiltonian evolution of the system. So if you wish, an analogy would be this is the ideal hydropower, and this is the viscous part. Okay, and notice that the noise term actually does depend on it's a function of the stochastic variable, and this is in the literature called as multiplicative noise, and you might actually notice that I haven't specified any prescription to tackle the Langevin equation, but I will not go into those details. They're described in our paper, but the upshot is that as long as you provide the correct physical input, you can use whatever prescription you want. You can use Ito, Stratonich, you can make your own prescription. It doesn't really matter. And the physical input is actually the equilibrium distribution. Okay, so now one can study this problem alternatively in a deterministic way. And for this problem, it's actually possible to derive any deterministic evolution equation for the distribution function. So this is the Fokker-Planck equation. And that describes how the initial probability distribution evolves into the equilibrium distribution. And as long as one specifies the entropy or the equilibrium distribution, so which is the physical input, again, you're free to use whichever prescription you want. Okay, and I think that I implicitly use Ito here. And again, I can define a generating function whose log I differentiate in order to get the nth cumulant. Okay. Now I'm interested in deriving an evolution equation for these cumulants. So those are my main objects. Okay. All right. Now from the Fokker-Planck equation, I can actually derive a formal equation for the generating function itself. And if I expand this in mu and look at the coefficient of mu to the n term, that coefficient will give me the evolution equation for the nth cumulant. So on the left-hand side, I will have Gn, the nth cumulant, of course, decorated with indices. On the right-hand side, that would be the time evolution. So for example, if I look at the n equals 2 term, on the left-hand side, I will have the 2-point function. On the right-hand side, I expand this thing here, and I have all these terms. So notice that on the left-hand side, I have the equation for the 2-point function, but on the right-hand side, I have the 2-point function, 3-point function, 4-point function, all of them. And this is the same for all the higher point functions, which actually is a problem, because I have now infinitely many equations, all of which contain infinitely many terms on the right-hand side, which might actually be a little scary. However, the saving grace is that I'm not interested in some random fluctuations. The fluctuations that I'm interested in are actually thermodynamic fluctuations, which are controllably small. And that sort of expansion parameter is given by the volume of the system. So these deviations from equilibrium are, which I call delta Q here, are actually suppressed by the entropy to the second derivative of the entropy to the power 1/2. and entropy scales with the volume. Therefore, each sort of deviation from equilibrium delta Q is actually small, which I quantify by epsilon, which is the inverse volume. So this epsilon has nothing to do with the epsilon expansion of RG. It's just a small number. Okay. So then I can figure out how, so because each delta Q scales as epsilon to the 1/2, the correlation function, which contains n delta Q's, scale as epsilon to the n, and the cumulants actually are even further suppressed because these are the connected components, and you can sort of work out, for instance, the fourth or the correlation function is dominated by G2 squared. However, the fourth cumulant is actually further suppressed and so on. Therefore, I obtain a truncation scheme where now for each correlation function on the right-hand side, I only have the lower point correlation functions. For G2 on the right-hand side, I only have G2. For G3, I have G3 and G2 and so on and so forth. So these equations can be solved now iteratively, right? So now it's actually useful to come up with a diagrammatic way of expressing these equations. So this diagrammatic way is as follows. For each G, I denote a black dot with some number of legs, and the number of legs is given. So the 3-point function will have 3 legs, 2-point function have 2 legs, 4-point function have 4 legs, and so on. The second derivative of entropy will be denoted by a hollow circle. Again, third derivative will have 3 legs, fourth derivative will have 4 legs, and so on. Same with the Onsager matrix, and when I differentiate, I add more legs. Now, if I look at the 2-point function on the right-hand side, I have S double prime times G, which is, this is S double prime times G, plus a delta function, which I just denote by a single line. For the 3-point function, I have 2 terms. This term is actually the same as the one that appears in the 2-point function. And I have S double prime G3 and 2 G's, which can be packaged like this. And notice that each of these terms are 0 separately in equilibrium. So I describe, or I denote like a half-filled circle to denote those terms that vanish in equilibrium. Okay. So then,
just a warning that we have 25 minutes into the talk.
Oh, my timer says 22 minutes, but I think I started a little early.
Yes, okay? You did. Yeah, 3. I don't want to rush you too much, but just making you aware.
Yeah, I'm coming to the final. All right, and now with this diagrammatic sort of approach, one can write the evolution, the sort of equations in these nice diagrams, and this is sort of useful to go to higher orders and loops and whatnot. So now one can apply this to the problem of nonlinear diffusion. I'll just skip the details, but this is basically taking the equilibrium limit. Now, instead of a finite set of variables, I have fields which are labeled by a continuous variable x. I have the standard entropy function whose derivative is the thermodynamic conjugate of the density, which is the chemical potential, and so on. My Langevin equation is basically the diffusion equation, where both conductivity and alpha are some non-trivial functions of the density given by the equation of state. And also the noise is a function of the density as well. And now I'm interested in the evolution equation for the higher point cumulants, which I can use this diagrammatic technique that I described earlier. There's one technical step which I'll skip. We generalize the notion of a Wigner function to higher point functions, where I have the background scale denoted by x and several sort of wave vectors that correspond to the fluctuation scales. I will skip that. And this is the main result. So these are the evolution equations for the second, third, and fourth cumulants of these nonlinear diffusion problem. And I want to make 2 comments here. Close to the comment number 1 is close to the critical point. This is the slowest mode, which is the dominant mode. where n has to be replaced by, of course, the entropy per baryon, and the gamma relaxation rates has to be replaced by a couple over Cp and so on. But these equations do describe the evolution of the higher cumulants in this hydro plus regime. And the second comment is that there are terms which contain the derivatives of lambda, which are due to multiplicative noise, and actually they are important where the critical point is scaled in a way that they're not negligible compared to the other terms. Okay? So with that, let me conclude. So I introduced deterministic formalism to tackle the non-Gaussian cumulants. There's a controllable expansion parameters by which these equations can be truncated, a generalized Wigner function, and we're still working on the full hydrodynamic evolution of the higher cumulants, but the nonlinear diffusion does apply to the slow zone near the critical. Okay. So that's all. Thank you.
Thank you very much, and thanks for staying in time. Very good. So we have, I see one question already listed, so let me take that too. Actually, let me start with Gabriel's question.
Hi, I hope you can hear me.
Yes, yes.
So it's just a very naive question regarding the beginning of your talk. So you're always discussing equations for stochastic hydrodynamics, like a continuity equation, like ddt of I plus diverge of J equals 0, or with some stochastic force. So my question is, usually when you take Navier-Stokes, relativistic Navier-Stokes equation or Iso-Struth equation, or any equation of that form, and you write them down explicitly, usually you get also second order terms in time derivatives, right? So the Navier-Stokes equations are actually second order in time. So would that affect this reasoning that you are describing here, which appears to be more like a non-relativistic kind of equation?
No, not really. These are so on the left-hand side, you will have. I mean, in the relativistic case, you have, you'll have u dot d mu, sort of like a sort of Lorentz covariant form. But no, these do apply in the relativistic case. What's non-trivial for the non-relativistic case? Sorry, for the relativistic case is that, well, I didn't go into the details, but when I describe, let's see where, yeah, when I describe these fluctuations, what appears so actually I wrote down the equations for the equal time correlation function. So now defining equal time in the relativistic case is actually tricky, and that's why in my equations, like for instance, I don't here. In the equations that I wrote, I don't have an ordinary derivative, but this is some form of, we call it confluent derivative, right? And this is a new type of derivative that sort of takes into account all the sort of Lorentz boosts and whatnot that you have to make in order to satisfy the Lorentz covariance. But in terms of the order of derivatives, I don't think there's any problem.
Because if I just can, one small comment, Uli, I apologize. So, because that's actually my question. Like, it appears to me that you go to the local rest frame of the fluid, where indeed the equation is first order in time, right? And then you try to take into account all the other effects of the Lorentz boost with these kind of derivatives. But the fact that the equations changes order, so there are additional solutions. For example, if you are in local rest frame, there's just first order in time. So it appears to be one type of set of initial conditions. But you go to a general frame, you'd have more information because it changes the order in time. And you're saying that this is taken into account also by this covariant derivative that you introduce.
So I think what you have in mind is some form of like Israel-Stewart type thing, which sort of...
No, Navier-Stokes itself. Navier-Stokes is second order in time as well. Right?
Navier-Stokes is non-relativistic equation.
The relativistic Navier-Stokes equation.
Landau-Lifshitz.
Yes.
Yeah.
Or Eckert.
Second order.
Well, they're different. So Eckert frame has a flux current, which has acceleration in it.
Mm-hmm.
So technically speaking, it's not really a good way of writing. So the idea The idea is that in the local rest frame, all derivatives there are in the local rest frame there are no time derivatives in the constitutive equations. The only time derivatives are in the conservation equation, and therefore the equations are first order in time derivatives.
This I understand, but in general frame they are second order. So you're saying that the Lorentz boost takes care of this difference in degrees of freedom?
Well, the equations are Lorentz invariant, so you can write them in the local rest frame, and they're first order in time derivatives.
But they're also opposed as well, as George showed, and stuff like that, right? So can anyone really apply this? So that was kind of my, I'm extending myself too much, so maybe I'll leave this for later. Uli will probably interrupt me soon. But that's kind of my general doubt here. I don't really understand exactly how this happens. So any kind of
the problems which you point out are exactly the same problems you would have for the usual hydrodynamics without noise. If this feature, I wouldn't call it a problem. This feature is a feature already without noise, and we know that the hydrodynamic without noise is a good theory in the sense that it predicts correctly the correlation.
It's unstable and causal. It's not a good theory, right?
It's not very good numerically. That's correct.
Yeah.
But it's
exposed. Okay, we really have to talk about this with time, because this.
I was just going to suggest this sounds very interesting, and this will fill up some of our discussion line later. So please hold the thought and bring the question back. Then let me give Søren a chance to ask his question.
Yeah, I actually have a couple at least. Good that we're on this slide actually. So here you mentioned kind of that you have to feedback the effect of the fluctuations into hydrodynamics, right, or into so to say the lower point functions, right? But if I understood correctly, this at the end of the day you eliminated by your power counting, right? So your fluctuations then no longer feedback in that case, or
yes. Okay, so let me clarify that what I mean. Okay, so there are two things here. So number one is this equation on its own. How does the 2-point function evolve in time, and especially like if you're interested in the signal sort of critical point and so on, you would be interested in the dynamics of the cumulants themselves as a function of the wave vector q and so on, and then sort of with some freeze-out procedure convert them into the fluctuations of the observable. That's separate. That's a separate thing from this. Well, now, so at which point you have to consider the effects of the 2-point function here. Well, if you are interested in going beyond the sort of the standard sort of viscous corrections, then the effect of fluctuations will show up between the first order and second order. So if you're interested in sort of corrections to the viscous hydrodynamics, then yes, then you should take into account the feedback of the fluctuations into the hydrodynamics.
Okay, but in what you had at the end, right? I mean, in these evolution equations, right, where you truncate, so to say, your hierarchies, right there, you kind of throw this out, then, right? I mean,
no, they look. So what I truncated is this is the evolution equation for the 2-point function, right?
Sure. Yeah.
So I truncate these guys, which are the 3-point functions and so on. So this will still give you some evolution of the 2-point function, which will then feed back into the hydro.
But that's not suppressed by the same power counting, or?
This is sort of, they are related, but it's a sort of a different. They are related. They are related.
Okay.
They're sort of related. Yeah.
And if I may ask my second question, Uli,
yes, please.
Yeah. I mean, then so since you're throwing out all these couplings between the higher order fluctuations at the end, which is, I mean, of course you have to do something. Does this? I mean, this must probably break down somewhere the closer you get to the critical point, no?
Yes. So all this truncation scheme applies where the volume divided by the correlation length is small.
Okay.
Sorry, large. So then, of course, in the sort of the middle of the scaling regime, where the correlation length is comparable to the system size, then of course all bets are off. But in sort of this hydro plus regime, where the correlation length is large but not as large as the volume or the system size, then it's you can still sort of study these. You can still isolate the slowest mode, which is the entropy from the next to slowest, or sort of this transition region. But yeah, in the sort of right next to the critical point, everything breaks down. Hydrodynamics completely breaks down, right? So you can't.
Okay, I don't see another immediate question here. Maybe I can ask a short question about your last slide before the conclusions. So yes, these evolution equations. So they are written down in the co-moving frame of the fluid cell, right?
Yeah. So these are actually yes. So yeah.
So have you given any thought yet what would be needed to implement them into a relativistic hydrocode where every fluid cell moves at a different velocity?
Yes. Yeah, so what should be done is, so notice on the left hand side we have dt's, right? But from what we found from the full relativistic hydro for the scalar sort of function, what the modification is that you replace left hand side with the Liouville operator. So for the scalar mode, the phonon velocity for those modes is 0. So but it has to be replaced by this, where this is this confluent derivative that we introduced. So you have to sort of take into account all these connection terms and so on. But this is this should replace the left hand side. Well, now another thing that we had was these terms. So that would give you the higher point analog of this equation here. So for the 3-point function and so on. What we don't have yet are these background terms. But sort of in this transition region to the critical point, this hydro plus regime, these background terms actually this decouples. The background terms become smaller compared to this term. So this nonlinear diffusion problem can be generalized by taking the appropriate sort of Liouville operator, which are.
All right, so before we move on, let's take the opportunity to thank Gökçe again. And I